Okay, so hello and welcome back. So in this video, we basically in these series of videos or in this playlist, we will talk about basically class 12. We will talk about class 12, part 1, chapter 3, which is about matrices. Now, of course, most probably you know that matrices are very popular in mathematics. They have applications all over mathematics in all branches of science, and the operations that we have in matrices then will be used in all branches of science, meaning that then basically using matrices you can get into physics and different planes and space and so on and so forth. And it's one of those concepts in mathematics that you need to learn in order to be able to understand and use the rest of mathematics. So we need to learn it well. And it's a very simple, basically it's a very simple set of tools that you can and of course have to, fortunately or unfortunately, add to your toolkit so that your mathematics is usable. Now, in order to motivate the concept of matrices, we will do a couple of examples. So, for example, suppose you wish to express the information that Radha has 15 notebooks. So, the information that I have is basically basically Radha has 15 notebooks. Okay. So you may express it as basically, you may express this piece of information in this notation. Meaning that you may put a pair of brackets and then write 15 in a pair of brackets. And when you write this, basically always with a notation comes some sort of understanding, meaning that, for example, when I write A and superscript B, for example, this is some sort of notation that we use in mathematics. What this means is that then in this notation, in this context, we call this the base, we call this the exponent, and for example, when we say that 2 raised to the power 3, what this means, based on the notation, what this means is basically 2 times 2 times 3, meaning that the base is multiplied by, times 2. That means that the base is multiplied by itself, the number of times determined by the number in the exponent, right? So that's what notation is, and of course notation is extremely important, otherwise there will be confusion and you wouldn't simply know what to do, right? And unfortunately, sometimes in mathematics there is areas where the notation is a little bit there is a little bit of confusion about notation. Some notation is used in this area of mathematics and other areas of mathematics, and commonly, and then that creates some sort of problems. And or sometimes in mathematics, for example, there is some notation that refers to basically, that may refer to two different things simultaneously. For example, there is some notation, for example, this notation and this notation, and these two notations might refer to different sets, or they might actually refer to the same set. So basically, every kind of text that you read, you need to be familiar with the notation that they use. And usually the texts that are meant to be understood by people, usually in the beginning of the text, they give you some conventions, meaning that they give that they tell you, at least wherever there is confusion, they say that whenever we write this, we mean this, and whenever we write this, we mean this, and so on and so forth. So what that means is that now this way of writing down this piece of information, this is some sort of notation that you can use. And again, with any sort of notation, there is some sort of understanding linked, meaning that I'm writing this notation. I'm using this notation with the understanding that the number inside the brackets, is the number of notebooks that Radha has. And of course, if I had this kind of notation, then of course I would be limited to a very low number of possibilities, meaning that then, for example, if I wanted to express the number of notebooks that, for example, Sarah has, then I would have to use, for example, another sort of bracket for Sarah. For example, then I would have to write 12 this way, use this notation, and write this as, for example, the number of notebooks that Sarah has. And the number of notebooks that, for example, John has would be, for example, something like, for example, 14, and, for example, this notation, and you would very soon run out of notation, basically, right? Now, but of course, this problem is not going to happen, because we will take care of all such problems in our notation in such a way that we will understand precisely what the expressed information actually means. Now, if we have to express that Radha has 15 notebooks and 6 pens, now suppose that now the information is, Radha has 15 notebooks. Radha has 15 notebooks and 6 pens. Right? So you might express this information as 15, some space, and then the number of pens over here, and then use the same type of bracket here. And you use this notation with the understanding that basically the first number inside the brackets is the number of notebooks, and the second number is the number of pens that Radha has, right? So that is the understanding behind the use of the notation, at least in this particular case. So we may express this as this notation with the understanding that the first number inside the bracket is the number of notebooks, while the other one is the number of pens possessed by Radha. Okay. Now let's make this a little bit more complicated. So now let us suppose that we wish to express the information of possession of notebooks and pens by Radha and her two friends, Fazia and Simran. So now we have, instead of one person, we have three people. So we have basically Radha, we have Fazia, and we have Simran, right? We have Simran, and we want to, and each of these people has notebooks and also pens. So Radha has a number of notebooks, she has a number of pens. Fazia, I don't really know if that's a masculine or a feminine name. So Fazia has some notebooks, some pens, and Simran has some notebooks and some pens. Now suppose that the number of basically notebooks and pens that these three people each have, or each has, is basically Radha has basically 15 notebooks. He has 15 notebooks and 6 pens. Then you have Fazia. He or she has 10 notebooks and 2 pens. And Simran has 13 notebooks and 2 pens. And 5 pens. Okay. Now you can basically write this information. You can write this information in tabular form. Actually, this is already you could say that it's already in tabular form. But the same information in tabular form, you can write it as, for example, you can arrange the names basically along the rows, meaning that you can write them as they are. So Radha, for example, and Fazia, and for example Simran. And then over here on the top, so you could have some table like this, for example, and write, for example, notebooks over here, and then write pens over here. And so I know that, for example, Rata has 15 notebooks. Rata has 6 pens. Fazia has 10 notebooks. And he has, or she has 2 pens. Simran has 13 notebooks. And Simran has also 5 pens. Right? So that is the information in in tabular form, right? And of course let me actually close this table so that it looks nicer, and then of course okay, and then I can basically write this way, and this is in tabular form. Now, and basically this information which we have expressed now in tabular form can be expressed as for example 15.6, 10.2 and 13.5. I can take these as rows, for example 15.6, for example 10.2 and 13.5, and use the same type of brackets to put them in the same brackets, right? So now you can see that since the number of basically elements of the number of elements inside the bracket is more than one, or more than, you could say more than one, then I get a number of rows and I get a number of columns. So that I have 3 rows here and 2 columns. So you can say that, for example, this is the first row, this is the second row, and this is the third row. And then you have over here from the left, over here you have the first column, and over here you have the second column, right? And so that's one way of basically that the combination of this table and this notation is one way of basically expressing the information that we have. There is of course another way of doing the same thing, right? Okay, so so then what we have here is so again in tabular form we can express this information this way, and in this notation, I'm not calling it anything yet, but in this bracket type of notation you can express the same information in the same format, meaning that 15.6, 10.2, 13.5, and a pair of brackets around the all of the numbers, and that's basically how you can express this information, with the understanding that, of course, for example, the first row contains all of the notebooks and pens related to Radha. The second row contains all of the notebooks and pens possessed by Fazia. I think Fazia is supposed to be written this way. And the third row basically contains all the notebooks and pens possessed by Simran. Or you could say that, for example, the first column refers to all of the notebooks possessed by Radha, Fazia and Simran, and the second column refers to all of the pens possessed by Radha, Fazia, and Simran again. So so that's basically one way of writing down this information. Now there is one more way to express the same type of information, and that is if I put the notebook and pens if I use them as rows and if I use these as columns. Meaning that if I say that, for example, over here I could have basically notebooks, I could have notebooks, and I could have pens here, and then over here I have basically Radha, I have basically Radha, Fazia, and Simran. And then I can write this in this form. I can write this in this form, and then this will be now the number of basic notebooks that Radha has is 15. The number of notebooks that Fazia has is 10, and the number of notebooks that Simran has is 13, and the number of pens possessed by these three people are 6, 2, and 5. 6, 2, and 5, and therefore I can rewrite this. I can rewrite this information as, for example, 15, 10, 13, and 6, 2, and 5, and put the brackets around them. And now you can see that this is my first row, this is my second row, this is my first column, this is my second column, and this is my third column. Right? And basically now I'm writing this information with the understanding that basically the first row refers to the number of notebooks of all the three people individually. The second row refers to the number of pens possessed by those three people individually. The first column refers to basically the notebooks and pens possessed by Radha. The second column refers to the number of notebooks and pens possessed by Fazia, and the second and the third column refers to the number of notebooks and pens possessed by Simran. And that is basically the difference here. You can see that over here over here you will get 3 rows and 2 columns. Over here you will get 2 rows and 3 columns, which means that the number of rows and the number of columns, as you can see, have been switched, really, or swapped. So that's basically one thing. And then now, by definition, basically an arrangement, some arrangement like this, for example, or some arrangement like this, or basically, or some arrangement of this kind. Of course, this is no good definition, but some arrangement of this kind is called a matrix. This is also called a matrix. Right? Now, as a definition, we can say that as a definition of a matrix, So definition 1 for this chapter, we can say that the matrix is an ordered rectangular array of numbers or functions. A matrix is an ordered rectangular array of numbers or functions. Numbers or functions. Functions can also be taken as the elements of a matrix. Now, the numbers or functions are called the elements or the entries of the matrix. The numbers or functions are called the elements or entries of a matrix. Right? Now, basically matrices, first of all, the plural for a matrix is the plural is matrices. The plural is matrices, meaning that as far as the word is concerned, and basically matrices are usually denoted, or well, I would say all of the time are denoted by capital letters, like for example sets that are denoted by A, B, C, D, and so on and so forth. So for example, you could have a matrix like, for example, A is equal to -2, 5, for example, 0, square root of 5, 3, and 6. Or you could have some other matrix B, for example, as 2 plus I, 3, for example, -1/2, 3.5, -1, 2, for example, square root of 3, 5, and 5/7. And you could have some other matrix C, for example, with 1 plus x, x cubed, for example, and 3, and cos x, for example, sin x plus 2, and tan x. Right? So these are all 3 different examples of matrices, of 3 different matrices. Now, in these examples, the horizontal lines of elements are said to constitute. So these are, you can see that here you have 3 rows, here you have 3 rows, here you have 2 rows. And basically the vertical lines constitute the columns of the matrix, meaning that here you have 2 columns, 3 columns, and 3 columns. So basically A has basically 3 rows and 2 columns, 3 rows and 2 columns. B has basically 3 rows, 3 columns, has 3 rows and 3 columns. And C has 2 rows and 3 columns. Two rows and 3 columns. And that brings us to the discussion of the order of a matrix. What that means is that basically we usually denote matrices by an order, and the order is determined by the number of rows and the number of columns that that the matrix has. Usually the number of rows of the matrix is denoted by lowercase m, and the number of columns of the matrix is denoted by the lowercase n. And we call the matrix as an m by n matrix. So, for example, this matrix is a 3 by 2 matrix. This matrix is a 3 by 3 matrix. This matrix is a 2 by 3 matrix. And what that means is that basically here you have 3 rows. Here you have 3 rows and you have 2 columns. Here you have 3 rows and you have 3 columns. And here you have 2 rows and 3 columns, right? So it's basically that simple, but then there is all kinds of notation that are used for referring to the order of matrix in general. So basically, as a more formal discussion of the order of a matrix, you can say that the matrix having m rows and n columns is a matrix of the order m by n, or simply m times n matrix. So you can say that a matrix having m rows and n columns is called a matrix of the order m by n, or simply m by n matrix, read as basically, and this is read as m by n matrix. So then, referring to the examples that we had, so you could say that those matrices were a 3 by 2 matrix, or a 3 by 3 matrix, or a 2 by 3 matrix, for example. You already know what I'm talking about. They were basically, in short, basically m refers to the number of rows and n refers to the number of columns. So for example, if you have 1, 2, 3, 4, 5, 6, 7, 8, 9, for example, 10, 11, and 12, and if this is a matrix, then you have 4 rows here and you have 3 columns here, and then this matrix is said to have, well, is said to be a 4 by 3 matrix. It's very simple, right? But of course, this simple concept has a lot of applications. I mean, you could say that the whole world that we have today around us is just a result of these matrices, because using these matrices, then you can have vectors, and then using vectors you will have access to the concept of space, not space in the sky, but space in our minds. And then using basically all of those matrices and vectors and space and so on and so forth, then you have access to all of the concepts of physics. And then you will have access to all of the concepts of, for example, computer science. And of course, our world would be completely different without the physics and the computer science that we have today, meaning that, for example, the video that I'm doing right now, the computer that I'm using in front of me is all matrices, meaning that of course matrices combined with other areas of mathematics, but then of course matrices are basically an indispensable part of this whole array of tools that we put together to build all of these tools, all of these basically all of the things that we have that come from science and technology. For example, I can remember that back then when we had the highest type of computer that we had, as far as I can remember, was an Intel 486 processor. It was an Intel 486 processor. It took the computer to, although it didn't have any software really installed on the computer, it was just DOS, Microsoft DOS back then. But it took the computer at least 20 seconds, 10-15 seconds to boot up. Even probably less than that, but well, it took the computer a long time to boot up. It had to check all of these different peripherals that it had, and then give you the prompt, and then you could write something on the prompt, and then it would do something for you. And back then, of course, there was no graphics, there was no video, there was no audio, there was no nothing. And then all of these tools that we have today as calculus, matrices, vectors, and all of these really basically wonderful concepts that we have today have come together, and that gives me, for example, that gives me the possibility to have, for example, 3 monitors in front of me. I can look on this monitor, on the other one, on this one simultaneously. My video is running. I have a pen in my hand, a digital pen using which I'm writing on this display. I have audio, I have video, I have the internet. The internet didn't exist back then. So, all of these things would simply not be there if basically, for example, if we didn't have access to these concepts of matrices. These are super important. Now, now you can say that in general, basically as an m by n matrix has the following rectangular array. An m by n matrix has the following rectangular array. So basically you have, first of all, the matrix is of course denoted by some capital letter. For example, you can say that A is such and such a matrix. And then the elements of the matrix, meaning that the numbers or the functions that you have inside the matrix, these elements are basically written in, usually, for example, if you call the matrix capital A, then these elements will be called lowercase b, right? And suppose that you have, for example, A is equal to, and suppose that A is a basically 3 by 4 matrix. This is you have 3 rows here and 4 columns, right? So then you can write lowercase a, and then you can have this, you can use the same convention that you use here, the number of the basically m by n, M refers to the row number, and N refers to the column number. And N refers to the column number. Meaning that basically relative to this element, the row number is 1, the column number is 1, therefore this becomes A of 1, 1, 1. The next element becomes A of, for example, 1, 2. The next element becomes A of 1, 3. The next element becomes A of 1, 4. Then the next element becomes A of 2, 1, A of 2, 2, A of 2, 3, A of 2, 4. The next element becomes A of 3, 1, A of 3, 2, A of 3, 3, and A of 3, 4. Right, so that is basically how you write a matrix. And basically then the number of rows in this column is basically 3, and the number of the number of rows is 3, and the number of columns is 4. And that's how you write a matrix, a particular matrix with a particular number of rows, a particular number of columns. Now, if you want to write this in a more general way, you can basically do the same thing you can write it as, for example, you can write it as basically A of 1, 1, A of 1, 2, A of, for example, 1, 3, and then you can just keep going until you reach A of 1J, right? J is the index that describes the column number. And supposing that you have n number of, and n basically that supposing that the number of basically columns is n, then the last element here becomes A of 1n. Now the next element that I have here, therefore based on this, becomes, for example, A of, this is the second row, so this becomes A of 2, 1, A of 2, 2, A of 2, 3, and then you can go all the way up to A of 2J and A of 2N, right? And of course you can just keep going in this direction as well, meaning that you will get to basically A of, now over here you can see that you have the column 1, the column 2, column 3, and over here you reach to column J. Over here you reach to basically to the row I, meaning that you have A of I1, for example, A of I2, A of I3, and over here you will get to A of IJ, and over here you will get to A of basically IN, right? And of course you can keep going in this direction, and so on and so forth. And the last row here, basically assuming that the matrix has m rows, basically this becomes A of M1, A of M2, A of M3, and all the way up to A of M4, all the way up to A of Mn. And that simply is the general way of writing a matrix of the order m by n. Right, so that is a general way of writing a matrix m by n. Now, instead of writing all of this business here, you can write, if this is matrix A, for example, you can write A is equal to, this is the matrix notation. This is the matrix notation. You can write it as A of Ij, A of Ij, A of Ij with the order m by n, where basically 1 is less than or equal to I, less than or equal to m, and basically 1 is less than or equal to j, less than or equal to n, because m is the maximum number of rows that you have of n, and n is the maximum number of columns that you have. And here basically I and j belong to n. And of course you know that m and n also belong to n, but that's not been written here. That's kind of understood. So now so what that means is that now you can see that in this matrix, the ith row consists of the elements a of I1, a of I2, a of I3, all the way up to a of I of n, basically, right? And the jth column in any matrix, in any matrix in general, consists of the elements a of 1j, a of 2j, a of all the way up to a of 3j, all the way up to a of basically mn. Actually, this is supposed to be, for example, this is supposed to be jmj, right? This is actually supposed to be a of mj. So this is m. This is supposed to be, so here that the row is m and the column is j, so a of mj. So then here you can say that the ith row, thus the ith row consists of the elements, so the ith row consists of the elements a of I1, a of I2, a of I3, all the way up to a of in, and the jth column consists of the elements a of 1j, a of 2j, a of 3j, all the way up to a of mj, right? So it's simple to see it over here. So in general, a of ij, and you can say that in general basically a of ij is an element lying in the ith row, and the jth column. And we can also call it I comma j in parentheses, I comma jth element of a, for example. You can call it this way as well, or you can call it this way. Now the number of elements in an m by n matrix, of course it makes sense that the number of elements in an m by n matrix is basically m is equal to m times n, right? Or basically you can say or mn basically, right? In case you might confuse this with the matrix notation, just simply m times n. Now the notation that we will use in this chapter is as follows. So basically we say that when we write basically A is equal to A of ij m by n here, this is to indicate that A is a matrix, of the order m by n, and this is note 1, and note 2 we shall consider only those matrices whose elements are real numbers or functions taking real values, meaning that we are not going to work with we are not going to get out of the real numbers here, I suppose, right? So we shall consider only those matrices whose elements are real numbers or functions taking real values. Okay, so that is one thing, and then we can also express any point. This is basically related to representing points in a plane using the notation of matrices. So we can basically represent any point x comma y in a plane by a matrix as, so this can be of course columns or rows depending on the situation. You can use columns, a row matrix or a column matrix, meaning that you can write this as x comma y this way, or you can write it this way, right? So for example, the point, if you have the point 0 comma 1 as a matrix representation, you would represent this as P is equal to either 0, 1, or you would represent it as 0, 1, this way or this way. And of course, you can understand that in this way we can also express the vertices of a closed rectilinear figure in the form of a matrix. So using this method, we can also represent the vertices of a closed rectilinear figure. Closed rectilinear figure means, for example, something like a parallelogram or a rectangle or a square or a trapezoid or things like that, for example, in the form of a matrix. So using this method, we can also represent the vertices of a closed rectilinear figure in the form of a matrix, right? For example, consider the quadrilateral. For example, ABCD with the vertices, for example, A is 1, 0, B is 3, 2, C is 1, 3, and D is basically -1, 2. And so if I want to represent this in a matrix of, for example, I can write it as, for example, I can put the x's and y's this way, meaning that I can write 1, 0, 3, 2, and 1, 3, and -1, 2. I can write it this way, or of course I can write it this way as well, meaning that I can write basically 1, 3, 1, -1, for example, 1, 3, 1, -1, and then I can write 0, 2, 3, and 2, 0, 2, 3, and 2, and write it this way, right? Now, you can call this x and you can call this y, for example, and then in this format, this is going to be point A. So A would be basically this point, this would be B, this would be C, and this would be D. In this format, basically 1, 0 would be A, this would be B, this would be C, and this would be D, right? So, as you can see, basically matrices can be used as a means of representation of vertices of geometrical figures in a plane, of course, right? Now let's take a couple of examples and see how we can use these matrices for different purposes. Okay, so now let's take a couple of examples. Let's suppose that you have the following information regarding the number of men and women. Women workers in 3 factories. In 3 factories 1, 2, and 3. Okay, so the information has been So these are the men workers and these are the women workers. So in factory 1 we have 30 workers, 30 men workers. In factory 1 we have 25 women workers. In 2 we have 25 and 31. And in factory 3 we have 27 and 26. Now if you want to represent this information, in the form of a matrix of the order, for example, 3 by 2, you would do simply the following. So you would write your information as it is in the table. So you would write this as 30, for example, 25, 25, for example, 31, 27, 26, and then you use the matrix notation or the brackets in order to show that, and then you have 3 rows and 2 columns, right? And that is, for example, you give it some name as well. Now, for example, the entry in the 3rd row and the 2nd column, this entry over here, that represents basically the number of women workers in the 3rd, for example, factory, or the entry in the 3rd row, for example, 1st column represents, for example, the number of for example, men workers in the 3rd factory, and so on and so forth, right? Now, another example that we can have is example number 2. Example number 2. And that is if a matrix has 8 elements. So a matrix has 8 elements. What are the possible orders of this matrix? What are the possible orders of this matrix? So we said that the number of elements of a matrix, is equal to m times n, meaning that, and m is basically the number of rows, and n is basically the number of columns, right? Which means that basically if since basically m times n is, in this case, is equal to 8, then you need to find out what are all the possible ways to write the number 8 as a product of 2 numbers, meaning that you can write 8 as, for example, 1 times 8, or you can write it as 8 times 1, or 2 times 4, or 4 times 2. That's all the possible ways of writing 8, basically. And so the order of the matrix could be a 1 by 8 matrix, or an 8 by 1 matrix, or a 2 by 4, or a 4 by 2 matrix. So that is basically the answer, right? Or suppose that, as another example, you want to construct example number 3, you want to construct a 3 by 2 matrix, a 3 by 2 matrix whose elements are given by A of ij is equal to 1/2 the absolute value of I minus 3j. So you have basically all of these rows and columns, so I can go from 1 to 3 and j can go from 1 to 2. So then basically your matrix would be some matrix A, for example, with A of basically you have 3 rows here, so you have all of these A's here, and you have 2 columns there. So this is 1 2, this is 1 1 actually, this is 1 2, this is 2 1, this is 2 2, and this is 3 1, and this is 3 2, right? And so over here you can see that, for example, your I is 1, your j is 1, your I is 1, your j is 2, your I is 2, your j is 1, your I is 2, your j is 2, and so on and so forth. So you have to calculate all of these elements one by one and put it in a matrix, meaning that I can write, for example, A of 1 1. Here I is equal to 1, j is equal to 1, right? So that then I can write that as 1/2 the absolute value of 1 minus 3 times 1, which is equal to 1/2 times the absolute value of basically 1 minus 3, which is equal to negative 2, which is equal to 1/2 times 2, which is equal to 1. Now A of 1 2 is equal to 1/2 times the absolute, I'm using all this relationship. So 1/2 times, basically, this is I, this is j, so 1 minus 3 times 2, which gives me basically 1/2 times the absolute value of 1 minus 6, which is equal to negative 5, which is equal to 5/2. A of 2 1 is going to give me 1/2 times the absolute value of 2 minus 3 times 1. Now this is equal to 2 minus 3, which is equal to negative 1. The absolute value of negative 1 is 1, so that is 1/2 times 1, which is equal to 1/2. A of 2 2 is equal to 1/2 times the absolute value of 2 minus 3 times 2, which is equal to, this is 2 minus 6, which is equal to negative 4. The absolute value of negative 4 is positive 4. 4 divided by 2 is equal to 2. A of 31 is equal to 1/2 times the absolute value of 3 minus 3 times 1, right? And that is equal to 3 minus 3 is equal to 0. 0 times 1/2 is equal to 0. And also A of 32 is equal to 1/2 times the absolute value of 3 minus 3 times 2, which is equal to, well, this is 3 minus 6, which is equal to negative 3. That becomes positive 3, so that is 3/2. And therefore A would be equal to this matrix containing A1 1, which is basically 1. 8 1 2 would be 5/2. A2 1 would be 1/2. A2 2 would be 2. A3 1 would be 0. And A3 2 would be 3/2. And that would be your matrix. So 1 5/2, 1/2, 2, 0, and 3/2. That is your matrix. And so that concludes this video. In the next video, we will talk about types of matrices. I'll see you in the next video, and thank you.